Try to lock it.
That's same link with the one. Yeah. So we're using the same meeting ID.
Then how we do formulate.
Yeah, analyst.
Yeah, right. This is the setting for. Yep.
Okay.
That's correct one.
Okay.
Sorry for the delay. There was some technical issues, but thank you for the. Still the moment here to have this. So let's continue. So we before the coffee break, we talked about the idea of Shapley value and then how computation of Shapley value is a challenge because of the combination. So how to set up the approximation of Shapley value? There are several key ideas. Indeed, there are major three key ideas so far. The first idea is that, well, we are not computing Shapley value instead, we are computing Shapley value in some specific situation. For example, data integration or machine learning, so on. In such a scenario, then the utility function or the game structure may have some specific characteristics that can help us to make Shapley value calculation more efficient. So one challenge, one opportunity here is that we may try to identify such opportunities to make the Shapley value calculation faster. The second idea is that, well, we do, for example, Monte Carlo approximation, right? And then when we do Monte Carlo approximation, then how to do a sampling is critical. And can we use smaller number of samples so that we can achieve the same accuracy in approximation? So this is about the sampling strategy. The third idea is that in some extreme scenarios, such as facultative learning, you don't have the luxury to consider many possible subsets, to do sampling, to run the process multiple times. In this case, how can we sacrifice some of the requirements in the fairness so that you still can derive some variation scores? So these three ideas are orthogonal to each other. You can apply them simultaneously to solve a problem. But let me show you some examples of these three ideas one by one. The first idea is that, well, in some specific scenario, the utility and the gain specific variation situation is different from the general Shapley value combination, where there's no any assumption. Indeed, in such an application, you do have some assumptions that you can utilize. For example, let's consider data integration. It is a data assembly game. The data owners try to collaborate together to ensemble the data set, to integrate the data set, and generate some target data in some predefined schema. And if a group of data owners can produce a data set, then any superset of the data owner can also produce the data set, right? And how such a property can help us build compute the Shapley value efficiently? That is the question. And the key idea is that we can do the divide and conquer. We can decompose the characteristic function, meaning the utility function and coalition to split up many similar cases. Okay, to be concrete, in many data assemblage tasks, a data set contains individual data records. And just imagine the situation you are trying to purchase a data set for data survey. For example, I want to purchase data about customers, potential customers, so that I can do, for example, advertisement campaign. Then the utility of each data record, meaning each potential customer, can be measured independently. Right? It can be measured, for example, each user worth $1. Or you can say, well, each user's value is proportional to its purchase capability or purchase history, whatever. And the total utility of one data set indeed is the summation of all the utilities of the data tuples in this data set. And with such assumption, then computation can be simplified. And one interesting question here is that you may ask, whether those assumptions real? And fortunately, indeed, in industry, people just dig it, although they don't have the right pricing model, but they just dig it. For example, like Azure Data Markets, they charge API call by each call, and they're summing up the cost of each tuple returned by the number of tuples returned by the call. Or in data rate, the data vendors, some data vendors just charge buyers record by record. So this is not a case by imagination. This is what happening in industry. Then how can we calculate the Shapley value easily? Well, one thing is that instead of computing the whole Shapley value of the whole data set, each owners versus the whole data set, one thing we can do is that we calculate the Shapley value of each owner versus each data record. And you may say, well, that's even more complicated because you decompose the whole data set into many data records, you increase the computation, right? No. The tricky thing here is that the structure of the computation changed. First of all, we can easily establish this relationship is that the Shapley value of OI is the sum of the Shapley value of this OI on every data record. Because every data record, the value, the utility is independent from the others, right? And I will avoid, I will, omit all the technical details. And if you are interested, you can look at the paper. But I will tell you the intuition. The intuition is the following: when you have the whole data set, you have many data owners. Therefore, no matter you calculate the exact Shapley value or you do the sampling to estimate the Shapley value, you still have to consider many possible combinations, many possible subsets. However, when you look at one data record in the data set, the number of data owners contributing to that specific data record will be dramatically smaller. Therefore, when you calculate the Shapley value of that data record, those not contributing to this record will get 0. And you have a substantially orders of magnitude smaller number of data owners contributing to one data record. And no matter you do the exact computation or you do the approximation, you still pay exponential cost, but total cost is dramatically smaller. And therefore, that helps you to save the total computation cost. Because the reduction on the number of data owners is by orders of magnitude. And the increase of cases you need to consider is linear because it's just the summation of all the records in the data set, right? And overall effect is still a huge reduction. Does this make sense? Okay. Another example. Well, in many situations, when we do the in the data markets or the machine learning model, either a task is complete or not. If it's complete, then the buyer will pay the full amount. If it is not complete, then the buyer will pay nothing. There's no partial payment. And in such a situation, yeah, it is different from the general case where partial payment may be possible, right? Because you have the utility. And this can be modeled as a simple game in cooperative game theory. And in a simple game, the Shapley value can be computed using the pivotal probability. What is a pivotal probability meaning is that, well, for one object O, it calculates all the other combinations where such a combination still cannot fulfill the task. But adding this O will fulfill the task. Right? In such a case, this O is called pivotal of this combination. Because this O will enable the combination from a failing collaboration into a successful collaboration. And you just need to sum up all the probability of such combinations where O is a pivotal. Then the problem becomes we need to efficiently counting because every combination has the same probability to appear. So calculating the probability is easy in the sense you just only need to count them. Now the problem is a counting problem, how to count those pivotal probabilities using minimal synthesis. What minimal synthesis means is that a synthesis is a subset. It is minimal if anyone in this subset is taken out, then the subset fails the requirement. Okay. So you can use, and when you reduce the problem to this stage, you suddenly realize, oh yeah, if I can write a subset, a successful subset, as a conjunction of items, right? Semantically, if you treat each participant as one item, and then the conjunction, meaning these two parties, these two players collaborate, right? And then synthesis, meaning these several subsets, these participants, they collaborate, they can complete the task. Then you give the value 1. Otherwise, you give the value 0. Does this make sense? And by the way, you are talking about digital logic 101. We are talking about binary expression, right? The binary logic, the Boolean logic. We all know very well. Yes, indeed, we reduce the whole problem now become the Boolean function decomposition, which has well-established results. And then we just try to say how we can decompose the how we can transform the representation into the normal form. Okay, and we have a problem to transform the monotone Boolean functions and then build decomposition tree and use this decomposition tree. We can count the minimum synthesis quickly. So that is a paper last year talking about using this approach to calculate the Shapley value in simple games efficiently. Any questions so far? I mean, I try to avoid all the mathematical details, but I try to give you the intuition behind. And don't be scared by all those formulas in typical when you read those Shapley value calculation papers. There's so many formulas, and each formula is so complicated and long. And typically they carry a very simple insight and intuition. Once you get the insight and intuition, things are so easy. Okay. Also, next month in ICT, we have another paper is that how can we do the Shapley value in preference queries. Yeah, this indeed is a very interesting paper, and we spent 1 year to educate the reviewers. This is a valid problem because the reviewers don't find the problem, don't understand why. The problem setting is the following. Suppose we have an Airbnb. Okay, I run those what Airbnb does, right? Okay, so you have different hotels, right? And suppose we have two dimensions. One dimension is the price. One dimension is the quality. And of course, you cannot find. I cannot say you cannot find, but it's very, very difficult to find a place is cheap and high quality. Typically, you need to do some trade-off, right? I mean, if you want the high quality, the price tends to be high, and if you want the price low, the quality tends to be low. Okay. So, suppose one customer buys, one night in a hotel, in an Airbnb. Okay. So we argue the whole revenue should not go to only the winning Airbnb. Instead, some part should be also given to those Airbnb who did not get the transaction. Then at least in 2 conferences, the reviewers said you guys are crazy. And economics is economics, it's not a computation, so you cannot do that. Why someone didn't stay in this Airbnb and you pay them? Okay, that's the magic of the market. You need to understand the market deeper to appreciate these location indeed is reasonable. You just imagine if you don't have such competing choices where the customers didn't stay. What will happen? It will happen is that winner can have the freedom to move their price as high as possible. Because they don't have condition, right? So they can set any price they want. That's not good, right? How to constrain them? In the marketing, not marketing, in the market mechanism, you need to set competitors. If you go price higher, then people won't choose you, will choose some alternatives. But those alternatives are not paid in this way, once the transaction is done, right? But they play the role of constraining the winners, how much they can get, how much revenue they can get, how much gain they can get. So those losing competitors are indeed an important component of the whole market. Does that make sense? And they should be paid. This is a whole model behind this paper. And now the problem is how to pay them. And then we use Shapley value in these preference queries, and it is very costly. But we observe several interesting properties. One property is that if each owner has only one Airbnb, then the problem indeed is a polynomial type algorithm. It's not exponential. Why? Because you have only a limited number of possible choices that the owner that the buyers can buy. It's not a combination. There's no combination there. I mean, again, skip all the technical details, but you can read out there. Okay. And we can generalize the situation if one buyer, owner can have multiple Airbnb, then we still can do the similar game, similar techniques, and we can compute it efficiently. So that's the basic idea here. And we can arrange, we can use the arrangement structure, partitioning the space with lines to compute this more computational geometric approach to the so the third idea, the third example I use here is that let's look at the machine learning process. Let's say if we train a large language model, okay, in one iteration, in one run of training, multiple data owners contribute their data. How much should I pay each owner? This is a very technical problem, right? And in sorry, that's the next. So this is a paper about the computation is that if you want to calculate the Shapley value, leave one out. It is very costly. And what they do is that they try to get train a lightweight predictor that maps an input to its importance score and use this lightweight predictor to replace the utility function. Because in a machine learning training process, if every time you have to train a model on a subset of the data set, this is extremely costly. So instead of training a model, you train another model to predict the performance, the utility of the model. So that's the idea here. And yeah, let me skip this one. Yeah. So very recently, I mean just a few days ago in IPER, there's another paper about Shapley value computation. It's a, well, I'm training a large language model. In each run, I want to calculate the allocation of revenue to each data owner. How can I do that? And of course, you cannot just ask them to get a subset and then do this training again. And there's no way you can run the same run of training multiple times on different subsets, right? So one idea, the key idea is extremely simple, but very elegant here is that, well, we can try to approximate the utility function using Tyler expansion. And smartly, and they find that the first order and second order approximations allow closed form expressions. Well, that's great because once it allows a closed form, then you can calculate that in constant time. You don't really need to do the subsampling, other things, right? And therefore, you can you just plug in any all the things, and then you can get a fast output. So this is the first idea. Maybe is that you look at different scenarios, Shapley values, and see whether those utility functions may have some specific properties that we can use to calculate them Shapley value quickly. The second idea is that, well, let's look at the problem from another angle. Is that we do the approximation using sampling, for example, using Monte Carlo approach, and then how we can compute the Shapley value. And as I said, it is more convenient to using the computation instead of the subset to do the sampling. Therefore, we use this formula. So the immediate idea is that instead of doing brute force sampling, we can do stratified sampling. People here, stratify sampling. The idea is very simple. Okay, you partition the samples into groups, and hopefully within each group the variance is smaller, and therefore you can get a better estimation, meaning the overall variance can also be reduced. And using smaller number of samples. And the heuristic is that if the subsets size are similar, and then their Shapley value, their marginal contributions could be similar to each other, and therefore each stratas can be a subset of can be the subsets of the similar size. In partition in this way. But the major cost here is the utility computation, because even with stratified sampling, you still need to calculate this marginal gain, right? And marginal gain is the difference between utilities, right? And the utility still could be very costly to compute. For example, if the utility is the machine learning model accuracy, then you need to really train the machine learning model, which is very costly, right? How to solve the problem. Okay, in the basic method, let's look at it. The utility of a random sample X can only be used by up to the size of X data pairs in the Shapley value. Why? Because once you calculate this utility S, right? And then who can use this one is that those small s in this big S, right? Assume they are sampled. So that's the number of times, maximum number of times you can reduce them. Okay. So one idea, indeed, it's a very simple idea. Most of our papers are very easy to read. Very simple idea is that, well, we can rewrite the Shapley value, Shapley value in this way. And here we use this special new term. It's called complementary contribution. Complementary contribution is very simple. You get a big S, which is a subset of the players, and then you calculate the Shapley value, the utility of this big S and the utility of these big set, the whole set of whole set of players minus these big S. So you pick a subset, you calculate the utility on this subset on the utility on the remaining items, players. Okay. Then the Shapley value of I can be derived in this way. What's the benefit? I mean, it's just a simple transformation. The benefit is that US and UN minus X can be used by every data owner in the data set. Why? Because, of course, for every data player in this X, we can use US and UN minus S, right? That's straightforward, right? But for every data players in this N minus S, then the complement contribution indeed is this UN minus S minus US. Just negative, right? And still they can use these two. Then suddenly the usage of the utility function evaluation will be dramatically improved because it's from the size of S to everyone. So that is the idea behind our whole paper in 2023 doing this. Simple. And later in June, we will have another paper coming up. Is another way to do this approximation. The idea, again, is very simple. So far, all the approximation is we try to estimate the Shapley value of every player independent, right? If you look at it. But by the way, they're not independent. Why? Because we have a balance requirement. Remember that? Because the Shapley value of all the players should be equal to the grant utility, right? So that remember the revenue V should be completely attributed to all players, no more, no less, right? This condition is not used in any of our estimation. Let's use it. How can we help us? Well, let me skip all the technical details, but give you one simple example to understand the opportunity here. Suppose you have three IID random variables x, y, and z. They follow the same distribution and normal distribution centered in 1/3, and with the standard deviation. Okay, so they sum up to 1. And we want to estimate their expectation. Okay, so method 1 is that we ignore this balance requirement and then we draw samples to estimate each random variables independently. That's what the existing approach does. You can play all kinds of tricks in sample to do that. It doesn't matter. Our idea is that because of their balance control, and then we can estimate the difference, pairwise difference among them. And when you estimate the pairwise difference, you can find, yeah, the variance can be smaller, can be reduced. What do you mean by variance is reduced? When you estimate a random variable, the variance is reduced, meaning you're either using smaller number of samples to get the same quality requirement, or you can use the same number of samples, but in expectation, you can achieve better quality, right? So, so that inspires our whole approach is that instead of estimating the Shapley value of every object, we estimate the difference, pairwise difference of the Shapley value between two objects. And then using these differential matrix based estimation, we can show that it can provide more higher quality estimation. Now, the third approach is that, in some situations, indeed, it doesn't allow you to do sampling at all. What can we do? So, one thing we do is that you have to limit the information, and then you have to do some other way to make a trade-off between data quality. The other requirements. For example, let's consider federated learning. Okay. By the way, federated learning is a very well-established area. Published thousands of papers on that, but not many deployed solutions yet. Of course, we can argue the reason could be, for example, privacy preservation things, but one important thing indeed is that, well, why should I put down my data in the, why should I participate in the federated learning, right? And then the incentive estimation is not established, and therefore, without an incentive people will be reluctant to put down their data. Okay, let's try to solve the issue. Now, the constraint is that in federated learning, I cannot run federated learning many times on different subsets. I have to run the federated learning one once, get the result, get the validation. How to do that? In each run, everyone here knows the federated learning framework, right? You take runs, in each run, you only query a subset, and typically a small subset of clients to contribute their updates. And then we consolidate the update and broadcast the update again in the next one, right? Therefore, we never get a chance to see all the possible conditions. Okay. And also, you cannot run federated learning many times as your sampling requirement needs. The idea here is that we try to turn this problem into a matrix completion problem. You just imagine you have a utility matrix where each row is one subset. So you have an exponential number of rows. That's fine. Each column is one row. Okay. So in the federated learning process, you will observe some entries in this matrix because you have somewhat in each one. You call a subset of times, and then ask them to report their update, and you know what the utility you get from their update. But you get an extremely sparse matrix, right? It doesn't matter. And let's make an assumption is that this matrix is approximately low rank. What does that mean? That means if I have two rows, two subsets, they are very similar to each other, then heuristically, we can assume their contributions, their utilities should be similar to each other. Or we have one row, one combination, and in two consecutive runs, their utility should not change dramatically. Indeed, that's what why you take the learning rate to confine that in the learning process, the parameters won't jump too much, right? You want a smooth learning process, right? So we have experimental results showing indeed in practice learning process, these assumptions hold, and therefore this matrix is approximately low rank. Once you have this requirement, then once you have these assumptions, then the problem becomes, I have a very sparse, approximately low rank matrix. Fill it, because when you complete this matrix, of course, I can know I have the estimation of the utility in each run of each possible subset. Then I can derive their contribution scores accordingly, right? No matter you use row-wise average or whatever. So let me skip the technical detail. That's the intuition there, and they have two papers. The latest one in last year I cleared is to how to solve the problem in this way. Yeah. So in evaluation, the basic idea is that we try to observe the harmony between cooperation and the fair, efficient data valuation, and then the more we understand the structure of the cooperation in data assemblage, the better we can provide a fair and efficient valuation. There are many very nice studies about the efficient computations of the specific types of queries, and that can help us to get better ideas how to do such structured computation. Okay. And typically the representation and the structural decomposition are powerful tools here, because once you get the right representation, once you have some way to decompose the structures, then it may give you the opportunities to do divide and conquer. Okay. That wraps up the section on valuation, pricing, revenue allocation. Any questions? Any discussion? So we still have two more sections to go, and I will just try to give you the general ideas in intuition. So in addition to core mechanisms in the data market, we still need some supporting mechanisms. For example, the distribution, security, privacy preservation is one important group. And limited by time, I will only focus on the privacy preservation, but let me first very briefly mention distributed data and AI markets. And as I talk about the data market concept at the very beginning, data market typically may have many owners, many pieces, and many forms. And therefore, it is distributed in nature. And also models are deployed in a distributed manner. The sharing and the discovery and integration and are also distributed. Okay, so the challenge in distributed data and AI markets is that, well, data and models are very heterogeneous, no matter format, quality, standard. And also in distributed participants, one major concern is the trust and the security. Okay, and in a distributed context, how do you make sure the incentives are also aligned? This is a challenge. And governance from the outside of the market, and how to enforce the compliance across the distributed sources. And that's another important issue. So, but there are also a lot of opportunities for possible research in this direction. For example, federated learning and decentralized AI frameworks could be a big challenge and opportunities. And I just talk about how to do the Shackling value calculation in the federated learning context. And there are a lot of other issues unsolved and interesting. And also, more and more data markets, they use blockchain and smart contracts for trust and transactions. And in such a context, how can we do the, for example, data pricing? How do we do the pricing and or the customer, buyer and seller, connection is another challenge. And the privacy preserving techniques, we'll talk about that later. Is another challenge. Yeah. And similarly, security, there are a lot of challenges. For example, data breach, unauthorized access, model theft and intellectual property risk, adversarial attack, lack of standard security frameworks. All those are issues for data and AI markets. There are several ways to do that, such as end-to-end encryption for data and secure multi-party computation. For example, remember we talked about the consortium approach, where the data station approach. Essentially, you have trusted, secured third party to conduct the computation, and robust authorization and access control, and all those techniques may be used. So those are the opportunities too. And for example, one hot topic could be AI specific cybersecurity solutions using decentralized technology like blockchain and so on. Now, let's go a little bit deeper into privacy. The privacy in data and AI markets are indeed very interesting. First of all, there are many different parties here. We may have data and model owners, third parties described by the data and owner, and data or model buyers. Each party has its own perspective in privacy. Okay? I'll go deeper to those. And also, there are a lot of different interactions. For example, supply demand matching. And in this matching, you want also preserve privacy. And data and model delivery and data model storage, you all want this privacy preservation. The key here is the trust. Should the privacy, privacy preservation is a very interesting concept here, and particularly in the data and model market context. Should we treat privacy as something purchasable, sellable? So that will allow you to consider problems in two different settings. One setting is that no, the privacy should be 100% preserved to the quality required. For example, differential privacy with the standard. Another setting is that, yeah, indeed, privacy can be purchased. And therefore, the price of the data and the model performance will be a function of the privacy guarantee. Okay. And what kind of privacy regulation and the impact on the welfare and the verification cost is also an important issue. But in data markets, privacy preservation, of course, is a hot topic. Not only for the market itself, but also for people outside the market. They look at it, they're very concerned about that. Any transaction in the data market may disclose privacy for different parties in many different ways. In many situations, they may disclose privacy beyond the typical way to say that even parties not involved in the transaction, their privacy may be still disclosed. For example, privacy of buyers. That is a question pretty open. When I say I broadcast my need to say I want to purchase the data about customers in this specific group, and my competitors may observe my broadcast and suggest, yeah, you may try to develop new products in this stage. Therefore, I'm disclosing my privacy, right? Or privacy of the provider of the information goods, right? And for example, if we may have hospitals, and one hospital may, as when they sell the data product, they may disclose the, for example, performance of surgery of this hospital, which is considered the privacy of the hospital. And also, it may have the privacy of the third party involved. For example, you are talking about privacy, you are talking about a data set about a set of customers. And then those customers, they do not involve in this transaction, but their data is described in the data set, and therefore their privacy may be disclosed in this transaction from one party to another party. And therefore, there are many privacy preservation approaches have been tried in this setting. This is a very active and interesting direction to go. Let's first look at data buyer privacy. And fortunately, there's only one paper there, so if you want to improve, it's very easy to improve. The idea is that, but as I said, the problem setting is very simple. A buy company, for example, purchase intent, say we are purchasing data sets related to riders of a specific age group, and it discloses the product intents, therefore there may be product privacy. To protect the data privacy, buyer's privacy, we may anonymize the purchase intent by including a larger data range, but not in the buyer's true intent. Now, when you do that, indeed, you have a trade-off between the cost and the privacy, right? If you want to protect your privacy very well, you just purchase the whole data set, whatever data, right? But you need to pay a lot. And if you want to save, and you only publish your true intent, but you don't protect your privacy, you need to get a better cut. Okay, so that's one idea. Another thing is model privacy. For example, you have data, I have model, and then I'm selling my model to you. But before you purchase my model, probably you would like to do is that, well, I want to I want to obtain the information about the performance of my model on your data, which is very fair, right? But you won't, you won't give me your data for a test, of course. Data is a privacy thing, right? Even you may not want to give a synthetic data set based on your data to me to get the test, because the synthetic data itself still reflect the distribution of your data, still can carry the privacy. At the same time, I won't give you my model to test on your data, because once you run my model once on your data, you don't need my model anymore. Right? And also there's another technique called distillation, and you can distill my model when you run my model on the data. So the buyer and sellers will start there, right? And how can the model owner provide some information about the reliable information about the performance of the model on your data? By the way, as I'm a model owner, I make up my model, I develop my model from my own training data, my test data. I have no idea about your data distribution. Therefore, I don't know what's the performance of my model on your data. And this is a challenge, is that these two things will be stuck. Okay. So that's how to solve the problem. One popularly used idea is that we can use some trusted third party. So we both give the model and data to this third party, and that third party run it. But the challenge is that this third party is very costly, and not only in terms of the cost of running a model on data, but also in terms of trust. How can we find this trusted third party? And also is the bandwidth of this trusted third party. If you think about, you have a large data market, you have so many owners, so many data products, buyers, then the third party won't be able to do the job. Okay. So one solution we are developing is a performance model. Instead of delivering the models to any third party, one thing I can do is that I try to learn another model. This model predicts the performance of my model. I know this sentence is a little bit weird, long, and hard to understand, but it is doable, right? Your model, I mean, you publish a model. This model does not do any prediction on the original data space. Therefore, the buyer gets the model, it cannot help the buyer to process its data. This model predicts the model performance of the target model on some input data. And therefore, the buyer using this model can obtain an estimation on the performance in their data. And in this way, of course, there are a lot of technical details how to ensure that the model performance is guaranteed statistically so that the estimation will be reliable. Yeah. So another interesting problem is privacy compensation. Remember, I talked about two things, two settings. One setting is that the privacy should be 100% guaranteed. Then we try to protect privacy. But another setting is that, well, the privacy can be solved. So this becomes a privacy compensation issue. And there are many studies on how to compensate on the privacy. And when the user, the user may disclose the privacy to some extent for some compensation. So there a lot of studies are listed here. For the interest of time, let's skip the details. Yeah, let me use one concrete example to illustrate what I said. Okay, suppose there is only one query. and the individual evaluation of the data are private data. And data owners are asked to report the cost of the use of the data. And then we can transform the problem into variants of multi-unit procurement action. And when a buyer holds an accuracy goal, the classic auction can minimize the buyer's total cost and guarantee the corresponding accuracy. At the same time, when the buyer has a budget, then the buyer can give an approximation to maximize accuracy under this budget constraint. So this is approach to do that. Okay. And another is like a posted price, like a mechanism. The idea is that we may have a set of data sellers in different types and associated of different cost distribution. And then we offer each user some contract with the expected payment corresponding the type. And if the seller have two choices, either take it or reject it, right? And if a seller takes the offer, the payment is determined by the seller's verifiable type and the associated payment in the contract. And therefore, using this mechanism, we enforce the seller has to be truthful, because otherwise it won't get the payment, right? Okay, so they can show that using some particles, they can ensure the absolute differential privacy here. Also, this may be related to contract design and any approach. So let's skip some of the details here. Okay, this is a very interesting study about the privacy and data utility. Indeed, if we have a pricing function, is this like as x be the price of x amount of data with privacy level s. Okay, so your price has two components. One is a setup cost to that level of privacy, and another is that the you have a coefficient here proportional to the amount of data you purchase. There are two types of users. One type is that aggregate information or pattern in data. The other type of user is I want to use the identified individual data records. And of course, they will have a very different nature here, because for the aggregation, to some extent, you don't care about the privacy preservation noise too much, because when you aggregate them, those parameters may, those noise may cancel out. You can still get quite good estimation. But if you want to get the individual records, then you're very sensitive to the noise, right? Because that noise on one data record will affect your decision on that specific data record. Okay. So the core idea here is that the data owner can identify the sensitive attributes in data and offer a low price of data without sensitive attributes, and charge for a higher price for data with sensitive attributes. And using this combination, it can help to accommodate the two types of data buyers at the same time in the same model. This is a relatively old paper, but it is very interesting to say, well, you have a privacy concern, and when you collect the data, then you need to estimate the cost of getting the data and pay for the compensation, compensate for the privacy, or I just don't get the data. I don't collect the data. And how to make such a decision. Indeed, there's some companies decided that it they don't collect data. They don't store your data. They just use it for the transaction and then they forget the data. And therefore, it is clear from the consequence. There are some centralized marketplace for private data. For example, Sterling is one approach to do such a system. So this is probably in the data market, the privacy part is the most active and well studied area, accumulated many approach there because it is there are many methods in privacy persuasion have been tried. Any questions so far on the privacy part? I mean the spotting mechanism part? Yeah. Yeah. Yeah, well, good question. Indeed, first of all, the two questions are very solid, very question, and that's met by many data markets when you try to establish the data model, the business model. The first question is that you need to introduce incentive into this process. As the whole tutorial here, we argue again and again, incentive is the key to establish a data market. You cannot imagine a data market without incentive. That's nothing, that's a mission impossible. Now, the second question is very important, is trustworthiness, and which we will talk about that in a minute. But the key here is that when you do a pricing, and then you need to know the utility. Therefore, when you buy the data, you do not buy the data to say, I buy the data so that I can use the data in whatever way I want to use. And in established data market models, this is not the case. The data market, data pricing or model pricing is always decided by, for example, we know the downstream applications. Because downstream application will define the utility. Therefore, you should have to say, even if you think about the separate value calculation, just say, okay, if the same combination can be used in multiple tasks. Indeed, you need to get paid from each task, get a summation. So I can, if my understanding of your question is correct, one challenge here is that no matter what institution you just mentioned, they want to say, I buy the data, I can use it in whatever way I want. And of course, the data sellers won't want to sell you the data like that. So that is what we discuss: the trustworthiness, the lineage, the governance. That is one important part in data markets. Without that, of course, if there's no trust, then the market won't exist, or the market will be extremely inefficient and costly. You also have a question? Yeah.
When the party want to collaborate or do some things, and at the same time, if we want to kind of price the data in, or kind of contribute contributions from different parties.
Yeah.
In this case, the pricing also become challenging because comparison is the issue, and it's hard to find kind of a trusted party to do this communication in the context of this problem. Also, it seems that if we compute price, it will also kind of disclose some privacy information.
Yeah, this is a very good question. So At this time, the solutions typically can be partitioned into two categories. One category is that I assume the privacy is already preserved 100%. For example, you have already applied differential privacy into your data set so that you just use a differential privacy preserving data set to participate in provision. In such way, then you just run the whatever pricing mechanics you do because you already protected privacy with the data source. Another approach is that you divide, you say, well, my privacy is some trade-off we can discuss, we can negotiate. And the negotiation process can be reflected in the mathematical model as you can decompose the pricing into two components. One component is more on the utility, another component is on the privacy compensation. Yeah, so you need some work looking at that. Yeah. This is a very valid concern. Yeah. Okay, great, thank you. So, thank you for your question motivating the trustworthiness. The major challenge is how to verify whether data models are delivered properly in the market as defined by the contract. Okay, and we need to, for example, show the evidence of ownership of data set and models, and how to verify whether contributions are valued and compensated fairly. Okay, I mean there are many more concerns, challenges, but I just say use two as example to show why trustworthiness is challenging. So let's first look at the interpretation of Shapley values. If I have two data owners, A and B, such that after all you decide to pay A higher than B, okay, how can you explain this inequality? So one idea we can explore is we can use a contractual approach. That is, you look at the resource owned by A that is not owned by B. Once you move this subset of resource from A to B, the Shapley value or the whatever contribution, evaluation, equality will fit. And you want to the subset as small as possible. So this is called contractual interpretation. So essentially, you just try to solve this optimization problem to find a subset here that this subset is moved from A to B, then it will flip the relation from this one A greater than B, then to A smaller than B. And this problem is an anti-hard problem. And how to do that? We can take a greedy approach. Instead of looking for a subset at a time, one thing we can do is that we look at the data elements one by one. And every time we only move one data element from A to B. And then this problem is easier, so we can use Thompson sampling to do this. That's our paper last year to solve the problem. Okay. And trustworthy also exists in model protection. For example, the challenge is how can verify that a model belongs to the owner. And an attacker can easily steal a model in many different ways. For example, can do model distillation. And if you don't know the idea of distillation, is very simple. You just use the unlabeled data and you have a target model, and then you ask the model to produce some label for you. And then you use these labels to train your student model, essentially only with limited number of training samples, you can learn the target models in a pretty good way. So how to tackle the issue? There are many different ways to do that. One approach is that we can try to add the bottom-up into the models. So adding bottom-up into data has been well done. essentially the idea is that, the data can be changed binary, the utility remains the same. For example, for image data, you can change, you can easily add a watermark into image data, but it doesn't affect the visualization effect. The model is difficult because the model are just parameters, right? And then if you change the parameter, you don't know what the parameter will affect your model. So one idea we used that was 2 years ago, indeed, is that the model will output two things. One is a class label, one is the confidence, right? The class label is something you better hands off, because if you change the class label, then you cause the performance issue. However, the confidence level can be modified minorly without any serious consequence. So we can add a small, very tiny component into the confidence level so that the model, if you fit the right data in this model, you can capture the watermark. However, if someone does not know this special pattern, then the person just cannot reflect the watermark in the model. So that's the idea. We essentially can get this teacher model into adding cosine signal there. And then we show that even you do distillation, because the confidence level will be also used by your student models, and the watermark still goes to the student model. In other words, I can detect the student model and show evidence that statistically unlikely that this model is independent from my teacher model. So this is an idea reported in GPI last 3 years ago in France. And then last year, a group in CMU, they use a similar idea and to add the watermark into large language models. And the idea still works. So that's one way to protect the models. Okay. A bigger context is that the auditing is important in data and AI market. Essentially, you need to ensure quality, provenance, just as your question said, and the compliance. And well, obviously, when you ask this question, I guess the compliance is not designed. Therefore, the users, the sellers, has no confidence on how the buyers will comply the requirement, right? And model integrity, fairness, performance, and the key is that we need to build trust among different participants, and also bias, vulnerability, and the unauthorized use. And unauthorized usage of model is a key issue in markets, because when you sell the data and sell the models, and you need to make sure only the people pay will be able to use it. Okay. Some key components of auditing framework, like the data lineage and the version checking, that's I just talked to you. And one thing I didn't mention before in this tutorial, but if the full course, definitely we should talk about is a versioning technique. I don't know how many of you know the versioning technique. Versioning technique is very simple. Okay, when you develop software, you develop a full version, right? All the functions will be there. And when you sell a piece of software, how do you make money? You just say, if you don't pay enough, I will cut many functions. Okay, I won't allow you to print out your picture. So I don't allow you to talk to connect to social media. And then if you pay more, I will unblock the function. I will unblock that function so that you can have the full function. And therefore, it is important to make sure the correct versions of those data, those models. auditing, fairness, transparency, and so on. And auditing is a big challenge, particularly on large data sets, large models, and also large markets. And how to do the auditing, what's the standard centralization is a big issue. And privacy preserving auditing technique is important, is not well developed yet. And also we are in the AI stage, right? How can we use AI and automation in auditing? And this is a problem that very few will mention, but this is also something we are working on. And I think it was talked about is know your customers. In finance, we all know we need to know your customers. This is a government requirement, right? But often in data and model markets, we do not have this formal requirement. But this is very important because you don't want to give the model or the data to the bad guys' hands. So how to identify the potential buyers and sellers and where so I don't know whether you know indeed there's a black market for data and models is a high volume, and that is well, you can hate it, you don't like it, but you cannot deny that it exists. So how we can make the ecosystem work and also get more and more wide markets instead of black markets, that is important thing to do. Okay. I guess, yeah, that's another big topic. I will just mention the concept. Yeah. Okay. So to summarize, essentially, I'll just give an introduction to the concept of data markets. There are places to facilitate shared discovery and integration of data resources and machine learning resources. And if there are many different types of data markets that already exist in the industry. So there's not just an imagination that's already happening, and many technical challenge and opportunities. We talk about that. And we firmly believe data and AI markets are the next thing, big thing should happen, because we already have so many large language models, so many advanced models, and next, what's the next thing to be next? Probably AI and data markets would be a big thing. And there are many exciting challenge opportunities like evaluation, privacy preservation, and so on. And the important thing is not only technology, but also entrepreneurship, because there are a lot of things can be done by startups, for example. And the important thing is that, well, you have to build an ecosystem. Once you build an ecosystem, you have a lot of opportunities there. Okay, that's up the whole thing, and thank you. If you have any question, I'm happy to answer.
Most of the downstream task is tested on is noisy label detection, but also one of the paper I recently read, they're saying the future direction could be applying Shapley value to incomplete data sets, where the inputs are deliberately amassed as some kind of like negative 999 value. I just want to ask your general thoughts about a Shapley value or measuring the marginal contributions of data points in incomplete data sets. Like, what's your general thoughts about that?
Yeah, very good question. Let me answer the question from two different angles. First is from the research angle. Shapley value is such a nice thing to have because it is provable fair, right? And also, it also is challenging enough to allow a lot of development there. Definitely for incomplete data, I mean, the setting is so general, so it doesn't matter is complete data or incomplete data, but it doesn't matter is the relational data or the graph data. You still also do the Shapley value. For example, one of my students is working on a problem is that, well, if we do the virus marketing, virus marketing essentially you select a set of signals and then you give them the information, ask them to propagate that, and then you see how converged the network dissemination is. In such a case, then what would be the value of each node here? At this time, it is very difficult to evaluate. Essentially, is that this legacy say I want $1 million. So how about 500,000? Yeah, it works, and then look at it. But this is unfair. I mean, not justifiable in many cases, right? So they try to estimate the importance of node edges. Edges meaning connections or completeness in terms of information dissemination. But the challenge is that Shapley value computation on the graph setting is extremely difficult. So to some extent, that's a very good research problem. But we should, that also leads to my second thought on that is that we should be open-minded. In many cases, maybe we don't need something as strict, as nice as Shapley. If we sacrifice some fairness requirement to some extent, we may gain a lot in terms of computation efficiency. Okay, for example, if you do leave one out, right? And we know leave one out, I already illustrated that leave one out has some loopholes, right? Can we just fix those loopholes to some extent instead of completely fix the problem? And then it may work in most of the cases. So those are the new directions to go. And another case, back to 2016, we have a paper, very interesting, is that, well, in a virus marketing setting, if I do not pay each person to examine the result, instead I give the discount of the person to purchase something, then what is the discount we should give? And the idea here is that you can have many mechanisms to do that. For example, you may have different levels of discount instead of real number, because a real number is such a range. You cannot do, for example, binary search because it's too big, right? So those would be mechanisms we can explore. I hope that answers it.
Thank you, Professor, for your thought-provoking and very inspiring talk, and it's very interesting. And I just wonder, like, in the data market, like, your way, like, pricing the data for each data owners, like, Shapley value, it's more like from a market level. But if I consider, like, will there be any, like, competition between or strategic behaviors between, like, data owners, for example, like, data set by consolidated for markets and again get more profit in the market and how that influences the real market?
Very good question. This is a great question. Indeed, that also related to mechanism design. Essentially, is that you should design the market in such a way that each player has to be truthful. I mean, is that each player should reflect its information in a truthful way. If the player does not disclose the information in a truthful way, it will hurt the player. You need to design in such a way. For example, when you do the auction, and if you do the, for example, second highest price auction, then it need encourage the players to do this kind of behavior. So there are a lot of studies on that. This is orthogonal to pricing and just say how they can express data, how they can facilitate the collaboration. And there's still many challenges on that. For example, if we have many players, many suppliers, and there are a lot of redundancy, and how can we choose the resources, right? And then we do not want them to say winner takes all.
Thank you.
Okay, I guess it's on lunchtime. Thank you again for staying here for 3 hours. For